Okay. So yeah, this can be hair. We can call it flower or whatever.
Can I have two hairs?
No, because they have odd symmetry. And switching two of them, by switching two of them, I'm getting minus that graph. So if two of them are on the same vertex, then switching them will not change the graph and it will be minus, so it's 0. I can have on different vertices, but not on the same. And there is condition at least one hair. Okay. There are some subcomplexes which are clear to define. No, differential. What does differential do? So on FGC, differential D is standard differential delta, which splits a vertex as usual. So splits a vertex and then connects edges which were connected to the late vertex to the new vertices. And if there was a hair on the vertex, hair comes to one of them. And also, I'm not allowed to do this. Okay, let this be here. There's a reason why I depict it like this, you'll see later. This must not go to this. I need, even though it's antenna here, I need to have edges towards both of them. So if I'm splitting this, some edges has to go, I'm splitting this, some edges have to go here, some edges have to go here, and there is antenna on one of them. But also this is not allowed. Okay? And there is another part of differential which adds one hair somewhere, sum over all edges. So if I have graph like this, delta adds here, for example, here, plus adding hair here, plus adding hair here, plus adding hair here. Okay, no, I'm sorry, this is not allowed because we need to have it on at least one. So I have it, so that it doesn't exist. Okay. There are easy subcomplexes. F fully hairy graph complex connected. Full hairy graph complex connected. It's clear, it's just connected. And there is what I call hairy graph complex. This is subcomplex of full hairy graph complex. This is subcomplex of FGC connected. And this, I have similar conditions as on graph complexes. Here, every vertex has to be at least trivalent, where hair acts as one valence.
The connected thing should be on the left.
Sorry?
Is 0 to equality? The C is for connected?
Yes. No, this is big C is for complex and small c is for connected. So connected to graph complex is subcomplex of everything. And this is by definition subcomplex. I'm not writing this because by definition I consider the same story as in graph complexes. I also didn't have C there and I meant connected. Okay. So at least trivalent. So here vertices are at least trivalent, and here is a valence. And there is a proposition, homology of full hairy graph complex connected is equal to homology of hairy graph complex. It's very similar to the old proposition. I will not show it because it's almost the same. And we don't have loops here, you see. This is exactly equal with no loops. So the proof is the same. You can do it by your own. Therefore, I continue. I have another proposition. This one I will prove. Homology of full graph complex, old one, is equal to homology of full hairy graph complex, shifted by one. Okay, you will see why I'm shifting. And the same is true for connected. FGC connected equals H of F HGC connected. Here you have the same story as there. Full hairy graph complex is symmetric power of full hairy graph complex connected. What was, there were some shifts, -2, 2. So if we know story about connected part, we know also about the whole part. And so I will here prove just this one, or this one is the same. Okay. I will have a map F from full graph complex to full hairy graph complex, which attached one hair to all possible vertices. So, okay, I can maybe write it down. So gamma is mapped to sum over all vertices in gamma. Gamma, here is this vertex V, and I'm attaching here.
Can you have two hairs on the same vertex?
No, because hairs have odd symmetry. So if you exchange them, you get a minus, and therefore it's 0. The same story as with the multiple edges. Okay. And here I will use the theorem. First, I will show what is a mapping cone. Maybe you know it. So if I have two complexes, C1, DC2, DC3, and D1, there is D here, D2, D3, and there is a map F. Where are chokes?
There.
Ah. Okay. Then this thing, C1 plus D0, C2 plus D1, C3 plus D2 and so on, where I have D here, F here, and D here. This is called mapping cone. Of this map F from two complexes, and there is a theorem, you maybe know it, that F is quasi-isomorphism if and only if mapping cone is acyclic. It's easy to check if you don't know it. So I use this here.
Yeah, the differential is what you wrote. It's the
Differential is D here, D here, F here. So from this map to this is a new differential. And it's easy to see that double is 0 because this commutes. Okay. So I use this there. Okay, so now let's imagine that these are graph complexes and these are hairy graph complexes. And D here is standard D, and D here is standard, okay, I called it delta, so let's call it delta. And D here was standard delta plus this delta. And F is attaching, so here we have delta, delta, delta plus big delta, and delta plus big delta. But this map F is attaching hair to every vertex, so it looks like delta also. So this can be also called delta, this F. It doesn't do anything. Just here we have no hairs, and this F adds a first hair, and here this delta adds another hairs, but it's always adding a hair. So, and this plus this, these are graphs with at least one hair, and these are graphs without hairs. So we can think of this as some graph complex, which we also allow that there are no hairs. So this mapping cone is nothing but, so this FGC was this, plus FHGC shifted by 1, that's why this shift comes, it's shifted by 1. I can call it FHGC0, what means full hairy graph complexes where it's allowed that there are no hairs. And I need to show that this is acyclic. And then I'm done. Okay. Now I use spectral sequences again. And spectral sequence, I will make a spectral sequence such that first differential is this delta. For example, on the number of vertices, because this delta increases number of vertices and this doesn't. So when I make a spectral sequence on the number of vertices, I have on one row full hairy graph complex 0 with just differential delta. And now there is another theorem. I mean, I'm almost done, but there is another theorem which I will use. If G is a finite group, C chain complex. And G acts on C. And is computed acts and it's computed with the differential delta. Then homology of complex, these are invariants under the action of G, is homology of C G out. It's easy to see. What's necessary is that this is a finite group. So what are these graph complexes? These are complexes where we at some point forgot the vertices, the distinguish that vertices are distinguishable. Here they are not distinguishable. But we can think of full hairy graph complexes before we made them equal, so we can put numbers on vertices. Then G, in this case Sn, where n is the number of vertices, just acts on it, and this will be my full hairy graph complex, and C will be the same thing but with distinguishable vertices. Okay? And if I want to prove that this is zero, it's enough to prove that this is zero. So at this time, when differential doesn't change the number of vertices, that's essential, I can distinguish them. And now I distinguish vertices. And I choose a vertex 1. I will use this story more often. When I choose a vertex 1, I can make a spectral sequence such that the differential, now it's FHGC0, but with distinguished vertices. And I can make a spectral sequence such that first differential is delta 1, which adds a hair on the first vertex. Just on the number of hairs of other vertices. So I make a spectral sequence on the number of hairs on other vertices, and then on the first differential, I will have this, where delta adds a hair on the first vertex. And there is H, which deletes hair on the first vertex, homology, H. So H deletes hair on first vertex.
And if there is no hair on the first vertex, it sends the graph to zero, right?
Yes.
H.
Sorry? H, yes. If there is hair, it deletes it. If there is no hair, it sends graph to zero. And you can easily see that H delta 1 plus delta 1 H is identity. If you have hair, then this will delete and add, so it will be identity, this will be 0. And if you don't have, this will be 0 and this will be identity. So in any case, it's identity. This means that this is a cyclic. Because of that, this is a cyclic. And because of that, the mapping cone is a cyclic, and because of that, they are quadratic. I'll just try to corollary. H of AGC 1 is H of GC. Now I'm on connected part plus big plus yacht greater or equal to 5 rot congruent to 1 mod 4 K 2 minus yacht. Okay, that's just two propositions. New title. I'm coming back to operads. Operad, full graphs with that pole and its suboperads. So this operand, full graphs with that pole, F with that pole, in arity N has, as before, is generated by graphs which have, as before, N, I will call now external vertices, which are distinguishable because they are inputs of the operand. They have some internal vertices. I will write them with a full dot and edges. Where degree of the edge is -1, degree of this internal vertex is 2. Yeah, that's it. And operatic composition goes in the same way as before. If I have this is gamma, and if I have gamma prime, and I want to calculate gamma composition on the point 2, for example, gamma prime, I put gamma prime into the vertex 2, and then connect all these edges which were connected to vertex 2 to all vertices, including also internal and external of the graph gamma prime in all possible ways. And this is a graded operad, and it's differential graded operad. Here differential is not 0. For the first time we have differential which is not 0. Differential on F graphs differential splits an internal vertex in the standard way we already know. So it splits internal vertex into 2 and connects zero. Internal vertex plus splits also external vertex, but now not into 2 external vertices, because I cannot with the fixed arity increase the number of external vertices, but I make one new internal vertex. So plus splitting plus splits X vertex into one external and one internal. So it splits this into this and attach in all possible ways, but I'm not allowed to have this without here. This I'm not allowed. But I am, sorry? Degree. Degree of a vertex is 2. And differential has to increase degree by 1. So if differential always adds another internal vertex and another edge. It changes degree by 2 minus 1, so degrees. No, it's not degree. This means I'm putting into the okay, this 2 is not a degree, this is number of input. And this means I'm putting into the input 2. Composition.
But okay, so you have a bullet up there and there is 3 equals 2. How do I see that?
No, it defines
You don't see.
It defines the degree of a full vertex of internal.
Degree of internal vertex is 2, in degree of edge is minus 1.
So the degree of that graph is 4 times 2 plus minus the number of edges, right?
Yes.
And out there, it's with only 0 for the external one, and you have at least 3, minus 3 for the edges, and then you add the white, so you add 2, and you add the vertex, so you remove 1, so you add 1.
Yes.
So it's of degree 1.
Differential has to be of degree 1 always. This was like before. Also in graphs, I had vertices of degree 2 and edges of degree minus 1 in graph complex.
And the external ones have degree what?
0.
Now 0, but when I will make complex, it will again be 2, sorry. Now I have fixed number of them, so I don't think they don't need to have degree, but when I will make complex out of operats, I will make them to have degree 2.
And why we don't want the last one?
This.
Yeah.
We also don't have, in splitting internal vertex, we don't have this. And that's a similar. Because you're, okay, so here I'm not defining differential as a Lie bracket with something.
But you are allowed to have one valent external vertex.
Yes,
right?
so this,
So the picture exists, but
this is allowed. Just this is not.
no, I mean that picture that you draw there is allowed in the complex, but it doesn't come from the differential.
It comes also from the different, this.
No, the other one. The one
Yes, it is allowed.
Okay, it's part of the. Okay.
Yeah, it can be killed. It doesn't contribute to homology. We'll see it. Because of the same story. Okay. So that's it. Did I forget anything? No? I will delete this. Okay, did I forget something? I have differential and composition. Okay, that's fine. And there are some suboperats. To be exactly, not to make something. 8, 7, here. Okay, some operand F graphs without fat poles. It's suboperand of F graphs with fat poles. So there are many of them, not to make. So here is F graphs connected, subcomplex of F graphs, just connected of these. No. Okay, maybe it's wrong. It's so F graphs, I will call them M. This is generated by graphs with no connected component of internal vertices. Made only of internal vertices.
So N is not a number. N is arbitrary.
No. Okay, so a priori here I'm allowed to have something like this. Where this is completely disconnected from external vertices. But in here I don't want that. And there is a proposition. No, it's not a proposition, it's kind of clear. I will not show it. That full graphs in arity N are what? Are full graphs no in arity N, tensor product K, which means there is no connecting component of internal vertices, plus if I have some connected component of internal vertex, but this is nothing but full graph complex. Now I have a degree shift here, this one, or if I'm right. No, -2. -2. Okay, so this connected component of internal vertices is nothing but full graph complex I had before. Therefore, we can have this kind of proposition. So it's here enough to investigate this and to know everything. And even more, okay, and I have another. Now what I hold graphs, subcomplex of full graphs.
So this shift by 2 is because full graph complexes have a global shift by 2? Or
Yes. Yes, they had a global shift by 2, so I can have.
What was full graph complexes? It was
graph without hairs, just I allow everything. One valent, two valent, disconnected vertices and edges. No tadpoles here, but I can put tadpole here, here, and here. Yes. And these graphs is subcomplex of full graph complexes. No, where you guess all vertices, all internal vertices are of valence at least 3 here. And there is a proposition I write here. Exactly. Homology of graphs equals homology of full graphs no. Proof is almost the same. Again, you kill antennas and two valent vertices in the same way as before. Can I use the whole blackboard because of the camera? Okay. Here. Here. Okay. Okay. Now remember Gerstenhaber opera D. It was generated by two elements, Lie algebra, Lie bracket, and wedge product. And I can define a map from E to graphs, where this is mapped to here, and this is mapped to here.
And the circle are really the circle.
External vertices. So in these pictures, I have no internal vertices, but they are allowed. We can check that this is really relations here hold also here.
I mean, it's an opera morphism.
Yes. So I mean, if I have X, wedge Y, Z, it maps to X, wedge Y. Okay, so X and Y can be something longer. So it's X, Y disconnected, and Z, I connect this to here or to here in all possible ways. But X, Z, wedge, Y, Z, this is equal. This is mapped to X, Z in all possible ways, disconnected to Y, Z.
Yeah, it's that's as a derivation.
No. No, I was wrong, sorry. I'm wrong. This is not equal to this. So this is equal to X wedge, Y, Z, plus Y wedge, X, Z. And this is mapped to X disconnected to Y, Z, here is in all possible ways. And this is Y I can write here, X, Z connected in all possible ways, but this is obviously equal to this. And you can check also Jacobi identity. Do you believe me? I can skip it. Okay, very nice theorem. I like this theorem very much. Proposition. This map, E, to graphs, is quasi-isomorphism. Proof. There is no there is no proof in here in this paper. Thomas is citing another work by Konsevich, I think. I don't know. But Thomas, yeah, it's Konsevich, but Thomas explained me this proof, which is easier. So what does it mean? So these are actually a bunch of statements. For every arity, it's independent statement that En to graphs N is quasi-isomorphism.
But
I have to prove this for every arity that it's quasi-isomorphism.
Is quasi-isomorphism, okay.
Yes, is QI. I prove it by the induction. Basis n equal 1. Here I have only identity. In E1, there's only one element identity. But in graphs 1, I have many elements. I have one external vertex. It has to be connected, and here I can have many stories, different stuff. But, okay, and identity goes to an empty one. So identity goes to this without anything else. And differential, this here is clearly quasi-isomorphism, because differential doesn't do anything to only this. And what I need to show that this, if I have something else, it's acyclic. But clearly, I need to make specular sequence, no? Here I make spectral sequence on the number of internal vertices plus 1 if this external vertex is more than one valent. Okay, so I'm calculating the number, I'm counting the number of internal vertices, and I count also this if it's not one valent. If it is one valent, then I don't count it. So, what I want to make? I want to make that, for example, this.
So you said you need strictly more than one valent, right? So
Strictly more. It cannot be zero valent because then we are in this situation.
because it's connected.
It's connected. Yeah, internal stuff has to be connected to something external, and since this is the only external thing here, it has to be connected. So if it's zero valent, it's everything. If it's so here is 1, 2, 3, 4, and I don't count this because it's two valent. But here, okay, this is okay.
But you are counting it, no? Because it's more than one valent.
Now, yes, here I'm counting that. Yes, you're right. So 1, 2, 3, 4, 5. And here I'm not counting it. It's 5 again. That's what I wanted. Because first differential of this specular sequence will exactly move this to this. Just detach everything from one. And then, therefore, I will have easy H in the opposite direction. So it's acyclic. Okay, this was the base. Now I have step. So now I have, this was big N. Now I have big N greater than 1.
So on a graph where
If-
more than one valent, it kills it.
Yes, so if 1 is more than one valent, it goes to 0.
Okay.
And if one is one valent, then I'm just contracting that one valence. Okay, now graphs N is, I call it C is equal to C0 of N, where here external vertex 1 is isolated. So it's zero valent or zero valent plus the rest. I can call it graphs and prime, which means one is not isolated.
So isolated means that it is not connected over internal vertices to some other external one?
It's not connected to anything here. So it means it's zero valent. So if one is zero valent, differential cannot make that property. And if it's not zero valent, differential also cannot make this property. So this really is splitting into two subcomplexes.
Once again, what was graphs?
This. I have n external vertices, arbitrary many internal vertices, and arbitrary edges between them.
But this was the vertices have to be connected, and that there would be
Yes, and there is no internal connected component, so everything internal is connected to something external.
You could have an isolated external.
Yes,
I see.
isolated external you can have. And every internal is at least 3 valent. External can be less than 3 valent. So,
No tadpoles or tadpoles?
not tadpoles here, but the same story will work, I think.
So yeah, another question.
Yes.
So in the definition of the map, you say the Lie bracket goes to two external vertices which you connect.
Yes,
So you can connect external vertices.
yes, you can. You can connect whatever you want. You can connect, if tadpoles are allowed, you can also connect these. Okay, so I am counting homology. I take homology of this.
One disagrees with the degree because here your bracket has to be of degree 1, and that's why it agrees. Degree -1.
Yes, exactly. This was, as you remember, of degree -1, and this is of degree -1. This was of degree 0, and this is of degree 0. Okay, so if I take homology here of everything, homology of this equals homology of this plus homology of this. But homology of this thing is equal homology of graphs n-1. Because differential just ignores 1 and works with the rest as if it's the one arity, one less. And so you remember that En dimension of En was n factorial. So since this is quasi-isomorphic by induction H of En-1, what's En because differential here is 0, dimension of this is n-1 factorial. So I know that dimension of C0n is n-1 factorial by the induction. Okay, so I'm working now with this part. And I make a spectral sequence again similar to this there. Spectral sequence, so on graphs prime, n, I make spectral sequence on the number of internal vertices plus 1 if 1 is more than 2 valent, more than 1 valent. Is not 1 valent because 0 valence I have there. And how does this spectral sequence look like? Okay, I will go and so it will look like this, where here B in B's, 1 is 1 valent, and in A's, 1 is more valent. And this map just extends just the same as this, just this map, first map of the differential, just moves this to this, and this is the rest under differential.
Sorry, once again, B are the guys which are just one valent.
These are part of the differential where external vertex 1 is 1 valent, and A is the more valent.
And what is the degree?
Degree is this.
Some text B1, B2, B3, so it's the degree, the number of vertices inside, or what is the
What's the difference
the-
between B1 and B2?
This number.
Okay. This is the degree of the filtration.
Yes. So I'm making filtration on this.
So P1 is just number of internal vertices. That is not plus 1. Or that's
So here we have 1 internal vertex.
But you say plus 1 if 1 is more than 1. Okay, because it's not more than 1 valent. Just 1 valent. So just 1 internal vertex.
Yes. Here's just 1 internal vertex. Yeah, 2 internal vertices, 3 internal vertices, and so on.
And A1 has, what is the degree here?
It's again the same filtration.
Again, the same. Yeah. So, but now here in A's, I count also 1 because it's more valent. So here A1 doesn't have internal vertices at all. It's just 1 is 2 valent.
So I think, okay, so on the...
For example, in A1, I have something like this. And this map maps it to B1, which is this.
This whole thing is here, the first...
Yes. On the first line, I only see this extracting from one internal vertex.
So for example, in A2, you could have one guy and one external, one internal, and
Yes.
just,
Here is 1 internal.
but you could not have one internal, one external, because then you would otherwise have to have at least one leg.
And so the number of externals is fixed, it's n, right?
Yes. The number of externals is n, it's fixed.
So in A2, you could, why
A2 means I have two internal vertices plus this, which is not one valent. So here I have one internal vertex.
One internal
And
vertex,
here I have two
so
internal
that
vertices.
The vertex labeled by 1 is at least 2 valent.
Okay, okay, because it's only about the vertex labeled by 1. Okay.
Yeah. So in Bn you have exactly n internal vertices, and one is one valent. Sorry, the
Exactly.
thing labeled by 1 is one valent, and on the A's, An has n minus 1 internal vertices, and the external vertex labeled by 1 is more than one valent.
Exactly.
Right. And on the zeroth page, when we see that the horizontal things, you guys now just do the same contract homotopy variable.
Yes, but we have to be a bit careful because here in B1, BK is, I just want to have the same notation. That's why I'm looking to this story. Okay. Is BK prime plus BK double prime, where this BK prime, I have one valent, but connected to internal vertex. And here I have one valent, but connected to external vertex. There are two possibilities. And I can make homotopy back only here. So now I'm investigating one row, which looks like 0, AK, BK, 0. But it splits as 0, AK, BK prime 0 plus 0, 0, BK double prime 0. And here I can have homotopy back. Only in this case, where this is maybe now, recall that this is at least trivalent because it's internal vertex, so I have at least two things here. And when I split, I will go to A. This will be more valent when I delete this. When I contract this edge, one will be more valent, so I will enter A. So I can have H here, and it's a cyclic because H, this D, call it D0, whatever, plus D0, H will be identity here. So this will be a cyclic. But this will not. This will obviously be this. Homology of this will be this. But what is this? I have 1, and here 2 to n. Here some structure, whatever. And this is connected to some internal vertex, external vertex, one of them. But what does differential make here? So I now know that, actually I should come back. So now I know that homology of these rows is just became double prime. So on the second page of this vector sequence, I will have everything 0 except B primes here. So second page will look like I have here zeros, and here are double primes. And this will be standard differential on B double primes.
Right, because you completely ignore the fact that one is connected.
Yeah. And that standard differential doesn't do anything to 1. Standard differential on this thing just does something on here. So homologies, again, we use the induction. Homology of, let's call it B prime, is homology of graphs n minus 1. but n minus 1 times, because this one can be connected in n minus 1 ways here.
So when you say n minus 1 times, it's direct sum, right?
Direct sum, yes.
Right.
Direct sum of yacht equals to from 2 to n, where yacht is where 1 was connected. K, I called it K. No, K skip, whatever, something. Therefore, dimension is dimension. I make much space here. Dimension of B prime double prime is n minus 1 times dimension of that. What's n minus 1 factorial? But therefore, dimension of graphs n is this plus what we had before, n factorial. Okay, now I proved that dimensions are fine. I didn't prove that it's the isomorphic. Map is not injective. Actually, it's easier to show that map is surjective. I mean, map on homology, not map there.
Yes. The other guy is much bigger.
Okay, we just look. We have to go through the whole thing with showing that it's surjective. I think I have it here. I will need the board.
So you said that it's complicated to see that it's network.
Yes. Why is it complicated? It's complicated because I have some two things there, and they obviously are mapped to two different things in graphs, but maybe they are in the same class. But we had, okay, we should go through the story we made. So graphs n is split in here. So it was split in C0n plus graphs n prime, where here one was isolated, here not. But En can also be split in E0n and En prime, where here one is isolated. Isolated here means that it's one wedge and the one is not in the Lie bracket. And you will obviously have map here and map goes here. Okay, and I have first part. I have gamma graph in C0n. What does it mean? It means that gamma is equal to 1, vertex 1, and gamma prime, which is in graphs n-1. So this is just one disconnected to this. Okay. Therefore, there is, because of the induction, I'm also doing this induction, some x prime, which is mapped here, which is in E n-1. It's not mapped here, but it's mapped to its class. And then obviously, here one wedge this, what is now in En, one wedge this is mapped to this. So this is mapped to this.
So you're supposing by induction that the map is surjective?
Yes. So I'm supposing that it's surjective, and I took gamma here, and I found something which maps to this gamma. This was the easier part. Let's do here. I have gamma in graphs n prime. It means that it looks like this. 1, and here is gamma prime, which is in graphs n-1, and this is connected to one vertex there. Okay, I showed that this homology of this, that it's quasi-isomorphic to B double prime. So instead of this, I can say B double prime. It's enough. So I can suppose that this is mapped to external vertex. That here is external vertex. Now, and I call this external vertex K. Now, because of induction, there is x prime in En-1, which is mapped here. And x prime is something in En-1. Now, in x prime, there is k somewhere. So maybe it looks like 2 wedge, 3, 4, 5, so on, and there is k somewhere. Instead of k, so instead of k, I put 1k. And what I get, I call x. And where is x mapped to? It's mapped to the same thing as x is mapped, so gamma prime, but x is mapped to, to gamma prime, but kth external vertex. Instead of kth external vertex, I have this with an edge and split it in all possible ways. Also when everything's here and when everything's here. But how does this map look like on this filtration? This x goes to something somewhere here and here, and I do the same after this mapping. I do this same spectral sequence, and everything is cancelled except this.
edges we distribute over 1 and k when you define the map, when you take the.
So by definition, this
What's the question? The question is why this expression. So you start with an expression with the x prime, and then you say you want to define the x by just bracketing with 1 inside where the k is.
yes.
And then you say, oh, and then I applied the map to b prime actually. To b double prime. What is this map? You say you send x to something.
So x prime was sent to x prime, to the gamma prime.
Yeah, but then
I chose x prime such that this was sent.
yeah, then you bracket inside of the big one, you get x.
And I'm looking where to this x is mapped.
Exactly, but why is it sent to the one where you distribute the edge going to k also to 1?
Okay, no, this 1k I can think as one package, which looks like this. And if this is a package, and I erased, but
So you're saying it's a map of operands? Yes. Okay, it's a map of operands, and you say you have defined this guy that you contract at some point instead of the rest. And now when you send it, you will also contract its image. Its image, you know that it's just this thing.
yes,
And then you contract this, and it's a regular contraction, which gives the distribution of the edges.
yes,
Okay.
okay, fine.
And so now you said at the level of the filtration.
On the level of refiltration, where this x will go, it will go somewhere to a.
So in level 1 of the filtration, it's just that one.
And it will maybe go to level 2. It will go to whole story.
Yeah, but the whole point is that
The whole point is
what
that
happens in B prime, right?
this will be in A. So x will go to something of this kind in A.
Sorry, I forgot what was A and B. Once again.
A was where 1
It's
more than 1 valent.
Okay.
B is where 1 is exactly 1 valent, but B was B prime plus B double prime, means where this 1 valence goes to internal and external. And exactly this x will go a bit in A, in bit in B, where in bit will go in B prime and bit will go in B double prime. But with this spectral sequence, A's and B primes will be killed. In the same way as this. So if it's mapped to this in A, so x, what's this, will be mapped to this in A plus this in B prime plus this in B double prime, where this is K. Okay, this will not be no, this we will not have, sorry, because it has to be connected to K.
But we could have an internal vertex, right?
Yeah, one of them, but
So you could connect K to an additional internal vertex, and the internal vertex could get some of the valences of the original K. Could this not happen?
You redistribute only the ones which arrive to.
no, actually X is mapped to something where there are no internal vertices. From the very, you remember the map from E to graphs, there were no internal vertices.
It's image.
Image is always external. So I will have this in A and this in B prime, B double prime. X will be mapped to this and this.
Yeah, but we're only concerned about.
But this is acyclic because of this complex. So what really survives after taking the homology is this part. So X as in the homology is mapped to homology of this, and homology of this is 0. Okay, so yeah, and that's exactly what we started from. We have chose gamma, and this is exactly that gamma we started from. So the whole story in short, we choose gamma in B double prime. We have to show that there is something which is sent here. Something in B double prime looks like this, where one is one valent connected to external vertex, let's call it K. And this is gamma prime, something in graphs n-1. With the induction hypothesis, I know that there is X prime in here, which is mapped there. In X prime, instead of K, I put 1K and get an X. This X is mapped to this plus this, but on the level of homology, this is cancelled, so only this survives. What's exactly gamma we started from? So the map is surjective.
That's very good because you stop the proof where the proposition begins.
Sorry?
The proof ended just before the proposition begins.
Yes. Oh, no. I have less than half an hour. Okay, now I will have complex E graphs.
E stands for?
E, that E, guest hub. So if I have P and Q operands, I can talk about operand P tensor Q. It's clear. And I can also talk about operand P tensor completed Q, where I am allowed to have infinite sums in definition of tensor product.
Q, no.
Oh, no. Q is another operand. Yeah. Okay, and I can have P tensor closed S Q. What will be by definition P tensor closed Q S? You remember what's this? Yeah, this is not operand anymore. It's a complex, and yeah, I just make on each level.
Vertices were distinguished.
Yes, at each level.
And here it's a product overall.
Yes. Okay, and if they were degree-graded operads, then this is a degree-graded operad, and also Lie algebra. And if it's a Lie algebra, we can have a Marko-II element and twist the differential to get a new differential. But I will be concerned in E tensor closed S graphs. And I will call it shortly E graphs. So what is this? What does it mean, this tensoring? So I have inputs here and inputs here, and I connect them somehow. So inputs here look like, for example, this. Wedge. Circle means input. Okay, so something of this kind is here, but here is something of this kind. Where these are connected to them. So element here in E graphs looks like this, where I have graphs, internal vertices, external vertices, edges, where external vertices are tensored with E, what means they form some operad in E. Okay. So just imagine on external graphs I make something like this. And differential is differential on E. There is no differential, and on graphs there is the internal differential delta, which splits internal vertex and external vertex. But I will have Marko-II elements here. And Marko-II elements will be alpha bracket will be this. And alpha wedge will be this. Both in E graphs. There is a reason why this is here and this is here. That's just. So one can check that they are Marko-II. And there is alpha, which is alpha this plus alpha this. And I have a new differential on E graphs D, which is differential delta on graphs, plus multiplication with alpha this, plus multiplication with alpha this.
Another bracket.
Sorry?
It's another bracket. It's the bracket of operas.
This is bracket defined on here in the natural way. So it is putting another picture of this kind into the vertex and then connect all edges in all possible ways and do on vertices standard thing what we are doing by this. And we can call this D this, and this is called D wedge, D bracket, D wedge. So D is standard data plus D bracket plus D wedge. Okay, I will not show it's more katana, I don't have time, but it's kind of easy. And now there is an inclusion of hairy graph complexes inside E graphs. Where hairy graph complex is mapped to exactly this. No? Now you see why I used this notation with wedge.
So you just wedge the external.
Yes. So just on hairs, we put external vertices and wedge them.
And which order?
The order doesn't depend because wedge is commutative. Wedge is associative and commutative. Okay, check that.
Hairy graph complexes didn't distinguish the vertices, right?
Yes, and also here nothing is distinguished.
Well, hairs are distinguished from usual stuff.
Yes, yes.
Hairs are distinguished from usual stuff. Exactly here they are.
Yeah, but you don't distinguish the hairs.
Yeah. Exchanging hairs moves to -1, but here exchanging hairs is exchanging these edges, or therefore it goes to minus. And we just need to check that differential is fine. But differential on hairs, as you remember, was standard delta plus delta. Differential here was standard delta plus d bracket plus d wedge. But what is d wedge? D bracket will here won't do anything because it will be killed, you can see. So if all external vertices are single, then this won't do anything. But this will do exactly what this does.
I don't see how the bracket acts.
D bracket is adding this in all slots.
Okay, so if you add this in one of the circles, one of the slots, you have a certain thing which is 0.
Yes,
Because
but then I add all this into here.
okay.
And this will exactly kill it if it's single.
I'm not sure I get it.
Okay, so if I have graph of this kind where all external vertices are free, single, and one valent, then bracketing with this will be what? Putting this into external vertex. So instead of external vertex, I put this, and since it was one valent, it goes to one of them. And sum over all internal vertices. Plus, minus actually, putting the whole graph in here.
Yeah, and then this. Oh, and this will distribute, you say, and it will distribute.
And this will be. Okay, no, that I was wrong. This is not killed completely. So this will be the whole graph. But this is connected to all possible ways there. If it's connected to external vertex, it will kill this. And if this is connected to internal vertex, it will be this delta. And yeah, so this survives and it's this delta, but this will be killed. Let's see why. Well, I don't know why.
So
For some reason, it will be killed. No, I don't have time. I mean, just check, you will see. So this is really an inclusion. And guess what? Proposition is quasi-isomorphism.
Spectral sequence, blah, blah. Next.
Spectral sequence, blah, blah. Okay, I have talk at 3, so I will skip everything here. Here, spectral sequence is very nice. I'm sorry I have no time, because there are more of them. So, well, yeah, just if you are very enthusiastic and you want to do it on your own, spectral sequence, first I have this, with this goes to delta plus d wedge plus d this. First I make spectral sequence which kills this and what? And this? Okay, I'm confused. First, you kill this and this. No, okay, sorry, no, I was right here because really this is 0 and d wedge because this is, no, I don't know. Okay, I'm confused which one is which, but so you make a first spectral sequence, and in the second spectral sequence you kill this, and you have 0 goes to what remains this, and so on. Okay, but okay, but then I'm finished because I don't. To go to Grothendieck-Teichmuller, there is a super long story. I will just tell what is done. So I have that graph complexes are through the whole chain, quasi-isomorphic to something what is called E-graphs, delta plus d wedge plus d this. Okay. But on this, I make a spectral sequence on the number of clusters. Clusters are these external vertices which are connected through a Lie bracket. So if I make the spectral sequence on the number of clusters, I kill this. And I will have a spectral sequence that I can compute this somehow. And I make a spectral sequence which on the second page looks like this. So if this is here a degree, and this is number of clusters, on degree 0 and number of clusters 1, I have k. It's also not proven in this paper, it's proven somewhere else. It's kind of standard result. 1, in degree 1, and 1 cluster, I have GRT1. Okay. So what does it mean? It's H1 of E graphs delta d this is GRT1. Thomas told me that this is almost the definition. I don't understand. Here I don't know. Nobody knows. And here are zeros. On the second line, I have here k, here zeros, here 0, and here I don't know. And in general, what we know is that, yeah, below this line, they are all zeros. And we will get something like this. And we can see that this is not killed by this, by story. Okay, 2 more minutes. Therefore, H1 of E graphs with the whole del D is, since here they are all zeros, these two things cannot be killed on any further page. So this is GRT 1 plus K. What is called GRT? Lie algebra. And we know that through what I proved here, that this is equal to H of H0, that was a degree shift of GC. That's the story how it goes on. So sorry, I only made this